Valence bond theory, NCRT part. We are discussing NCRT part. Actually, I am reading, you are listening, right? As we know that Lewis' approach helps in writing the structure of molecules, but it fails to explain the formation of chemical bond. It also does not give any reason for the difference in bond dissociation enthalpies and bond lengths in molecules like hydrogen. Try to remember this value. In most of the examples, it will come 74 picometers, and fluorine 155 kilojoules, 144 picometers. Hydrogen bond is stronger than fluorine. Remember this point. Although in both the cases, a single covalent bond is formed by the sharing of an electron pair between the respective atoms. It also gives no idea about the shapes of polyatomic molecules. Similarly, the VSEPR theory gives the geometry of simple molecules, but theoretically it does not explain them, and also it has limited applications. To overcome these limitations, the two important theories based on quantum mechanical principles are introduced. These are valence bond theory and molecular orbital theory, VB theory and MO theory. Valence bond theory was introduced by Hitler and London in 1927 and developed further by Pauling and others. A discussion of the valence bond theory is based on the knowledge of atomic orbitals, electronic configuration of elements. The overlap criteria of atomic orbitals, the hybridization of atomic orbitals, and the principles of variation and superposition. This is the basis for the valence bond theory, right? A rigorous treatment of the valence bond theory in terms of these aspects is beyond the scope of this book. That means you are not going to learn in class 11. No need. Therefore, for the sake of convenience, valence bond theory has been discussed in terms of qualitative and non-mathematical treatment only. Okay, questions also will come in the same way. To start with, let us consider the formation of hydrogen molecule, which is the simplest of all molecules. Consider two hydrogen atoms, A and B, approaching each other having nuclei Na and Nb, and electrons present in them are represented by Ea and Eb. When the two atoms are at large distance from each other, there is no interaction between them. Of course, when they are away from each other, no interactions. As these atoms approach each other, new attractive and repulsive forces begin to operate. Why attractive forces? Attractive forces arise between nucleus of one atom and its own electron, that is NaEA, NbEb. These attractions are always there. And second attractions are nucleus of one atom and electrons of other atom. Okay, now one nucleus is attracting other atoms' electrons. Similarly, repulsive forces arise between electrons of two atoms, AEB, and nuclei of two atoms, NaNb. Same charges repel, that is only mentioned here. Attractive forces tend to bring the two atoms close to each other, whereas repulsive forces tend to push them apart. So here it is mentioned, you can see plus charge, that means nuclei, these are the electrons of it. So between plus and minus attractive forces are there, plus and minus attractive forces are there, like that. It is mentioned clearly. These are the repulsive forces, between negative charges repulsive, between positive charges repulsions. Okay, now between opposite charges attractions, between same charges repulsions. Experimentally, it has been found that the magnitude of new attractive force is more than the new repulsive forces. So definitely they will come close. As a result, two atoms approach each other and potential energy decreases. Remember this point. Neat question. Ultimately, a stage is reached where the net force of attraction balances the force of repulsion and system acquires minimum energy. At this stage, two hydrogen atoms are said to be bonded together to form a stable molecule having a bond length of 74 picometers. Since the energy gets released when the bond is formed between the two hydrogen atoms, the hydrogen molecule is more stable than that of isolated hydrogen atoms. So simple line, atoms more energy, less stable. Simple line, molecules reverse, less energy, more stable. The energy so released is called bond enthalpy. which is corresponding to minimum in the curve depicted in figure 4.8. Conversely, 435.8 kilojoules of energy is required to dissociate 1 mole of hydrogen molecule. To break hydrogen molecule, this much of energy is required per mole. That means when these two are combining to form H2 molecule, this much of energy is released. See, this diagram will be definitely asked. See, bond length is 74 picometers. This is internuclear distance. At this distance, you can see it is with the minimum energy, and that energy is showing here 435.8. Okay, so distance of separation, this is attached, completely closely bond formed, going out completely separated. So you are breaking like this. Okay, minimum energy, maximum stable, this is the molecule. These are the atoms. You can see atoms are separated. It is overlapping is there. The potential energy curve for the formation of hydrogen molecule as a function of internuclear distance of the hydrogen atoms. The minimum in the curve corresponds to the most stable state of hydrogen. Right? This is most stable state. This one will make in another video. Right? Thank you.